Welcome to the lesson 3 under digital techniques. Our lesson for today will be logic gates. We want to look at logic gates. What are logic gates? Logic gates are the basic building blocks of any digital system. Um, it's basically an electronic circuit having more than one input and only one output. Now, the relationship between the input and the output is based on a certain logic. Now, based on these logic gates, the gates are named. And what are these logic gates? Logic gates, the basic ones are the AND gate. We also have the OR gates. And then we have the NOT gate. These are the three basic gates. From these gates, other types of gates evolve. Okay? Now, a digital system are said to be constructed using logic gates. These gates are what we have mentioned before, and we shall also have about 7 of them, which comprises from these 3. We have the NAND gates, a combination of AND and NOT. We have the NOR gates, combination of NOT and OR. We have the XOR and the XNOR gates. So there are what? 7 types of gates. There are 7 types of gates. So these type of gates are what you limited from the AND, the OR. You can see that from these 3, these are the foundation. Okay? These are the foundations where all these spring out from. Now we're going to see how these gates are drawn. We say that they make up inputs and have one output. We have just one output. So we can have more than 2 inputs. We could have 2 input and gates. We could have 3 inputs and gates. But definitely they will always have one single output. So let us take a look at the AND gates. This is how you draw AND gates. This is a 2 input AND gate with 1 output. Okay, so we have, let's say this is A and B. The inputs, the AND will be A, B. So the AND is just like the conventional multiplication, okay? Like A times B, we have it as the output. Another one is the OR gates. This is how we draw it, like an arc. 2 inputs, A and B, with a single output. And what is that? A plus B, but actually it is called A and B. Okay, that's how we pronounce it. Not A plus B. So it's A and B. This is how we draw the OR gates. So the first one is and this is what OR. And then finally we have the 3, which is the NOT gate. NOT gate is unique. It has 1 input and an output. So we some call this the inverter. So whatever thing you put here, it inverts it. And then we have it as what? A bar or A prime. So some text we have it as A prime, while some we call it what? A bar. Okay, so this is the inversion, inverting the input. That's what this 3 does. Okay, so this is the NOT. Now from here we can now combine to have the remaining ones, like the NAND gate. So the NAND gate is a combination of the AND gate plus the NOT gate. So we now add the NOT gate, this one. Okay. So this is how it looks. But for simplicity, we are going to now have A, B, bar. So for simplicity, it is drawn this way. is just a circle. Just draw a circle, and then you now have the output. So when you see this, you know that there is an inversion. So A and B will be inverted just like this with a bar. Okay? So for example, we have 1 and 1, we have what? 0. So that's the inversion. Now from here, we can also have the NOR gate. So this is the NAND, and then the NOR. We have the ARC, okay? And then we have it this way. And remember, we have a NOT. And this NOT is showing that it's an inversion. So this is the NOR, A, B, and then we have A and B bar. So can you see that? So this is the NOR gate. So we have 1, 2, 3, 4, 5, remaining 2, and the 2 is the XOR or XNOR. So how do we represent that? I'll clean this one so I can have where to draw that. So the first one is the XNOR, XOR. So still the same OR. We will draw our OR. But this time around, we make another additional arc at the back. So we have the A, B, and then this you have an inversion. A and with a circle B. So this is how it is called. So this is the X OR. Some will just write it as just E or some will write X OR. So we write it this way. Then the next one is the XNOR. So this is the NOR. So the difference now with the XNOR is that we have an additional arc here, just like this here. So once you have an additional arc here, okay, when we have an additional arc here, we now have it as what? XNOR. This is how we represent it. Then the output will be okay, same thing, X, C around it. So this is the logic gates. These are the fundamental logic gates that we have. And this logic gate, we are going to see how you can have more than one logic gate in a circuit. So you can have combinations of so many of them to achieve a certain output that is needed. Another topic we are going to be looking into is the Boolean variable and the truth table. Because under this logic gates, there's what we call the truth table, and then the Boolean variable. So that's what we're going to be looking next. Boolean variables. And truth table. What are Boolean variables? Boolean variables are zeros and 1. These zeros and 1 do not represent the actual numbers, but instead they represent the state of a voltage variable, or what is called its logic level. Okay, so we call it logic 0 or logic 1. Okay, so it's not different. We shouldn't see it as ordinary 0 or 1. This 0 could mean something like on, or let's say 0 for off, 1 is for on. Okay, on. We have this could be true or false. This is false, and this is true. This is no, this is yes. This could be closed, and this is open, or so on and so forth. Okay, these are what we mean by different logic levels. So we don't see them as actually number 0 and number 1. So it means logic 0 and logic 1. So when you say 1, 1 can be high. You know, I want the temperature to come high. When it becomes high, I put 1. when it is low, output 0. So when the system sees 0, it knows it's what? It is low or off. And when it sees 1, it's like on. So you can group in a certain voltage that goes probably into a controller. You could say anything from 0 volts to, let me say, 1.5 volts, give it a logic level of 0. And anything above 1.5, let's say from 1.6 to, let me say, 5 volts, give it a logic 1. So whenever the system sees the voltage between this, it outputs a 0. And when it sees something greater than that, it outputs a 1. Okay, so that's what we mean by Boolean variable, or Boolean, a Boolean. But however, there's what we call Boolean algebra. What is Boolean algebra? Boolean algebra differs in a major way from the ordinary algebra, the algebra of 1 plus 1 and all that we did in our mathematics, in that the Boolean constants and variables are only allowed to have only 2 possible values, which are 0 and 1. What are the truth table? What is a truth table? A truth table is a means of describing how a logic circuit outputs depends on the logic level present in the logic's, or rather in the circuit's input. Take for example, we have the 2 input OR gates. Take for example, we have a 2 input OR gates. Okay? And then we have A and B. These are inputs to the OR gates. And then we have an output. And the output is A or B. Now, what is the truth table? These are all possible values or possible value combination at the logic level represents at the inputs. And there's a formula for that, which is 2 raised to the power n, where n is the number of inputs to the logic gates. So, for example, the possible values of A and B that can go into these logic gates, which is the truth table, is represented by 2 raised to the power n. 2 raised to the power n is what? Raised to the power 2 is what? 4, because it has 2. So what if it has 3? 2 raised to the power 3 is what? 2 times 2, 4 times 2, 8. So it has 8 possible values. So for this, we have 4 possible values: 0, 0, 1, 0, 0, 1, 1, 1. You can see these are all possible values that can be here, A and B can have. And then the OR gate, that is A or B value, will be 0 or 0, will give you what? 0. 1 or 0 will give you 1. 0 or 1 will give you 1. 1 or 1 will give you 1. So this is what is known as what the truth table. All possible combination and their likely outputs. Okay? So when we look at that for the AND gate, okay, the 2 input AND gate with A and B, okay, A, B, A and B. Okay, we're going to also have 4 possible values, which are 0, 0, 0, 1, 1, 0, 1, 1. Okay, so this is 0 and 0 is 0. 0 and 1 is what? 0. 1 and 0 is 0. Then 1 and 1 is what? 1. So one can liken this as our normal algebra in mathematics, where we have to see it as plus, and this one as multiplication. Multiplication. That's times. So you can say 0 times 0, 0 times 1. Of course, anything that is times by 0 is always 0. 1 times 1 is 1. This can be seen as 0 plus 0, 0 plus 1, that's 1, 0 plus 1, 1. Here, 1 plus 1 will definitely be 1, not 2. So that's why we say that the Boolean algebra is different from our normal mathematical algebra. The next variable we are going to be looking at is the We have seen the OR and the AND. We look at the NOT. We look at the NAND. These are the remaining ones. The NOR, the XOR, and the XNOR. So let us see that for the NOT gate. The NOT gate, remember the symbol drawing is a very simple one. Only one output, and then at the output, if here is 1, here is 0. And if here is 0, here is 1. It's always inverting it. So this is the truth table for the NOT gate. Still remembering the formula, 2 raised to power 1 is the same thing as 2. So that's possible 2 states. So the next logic gate we'll be looking at is the NAND. Remember how the NAND was formed, which is a combination of the AND and the NOT. Okay, so which means our truth table can be in this form if we are looking at a 2-input NAND gate of A and B. This AND and NOT. So this is a NAND gate. So we can have the same possible output 0, 0, 0, 1, 1, 0, 1, 1. Okay, so if we decide to use the A or B, and then remember NOT is A plus B prime, or not equal to, or complements. So these are possible names that you can see it. Because some refer to it as prime, some refer to it as not equal to, while some refer to it as bar. So if we take this, we say 0 or 0, 0, 0 or 1, rather and, this 0 and 1 is what? 0. 1 and 0, 0. 1 and 1 is what? 1. Now, remember, it goes through a NOT, which is an inversion. So it's going to invert the whole thing. Okay? So inverting it means this 0 will become 1, this 0 here will become 1, this 0 here will be inverted to 1, and this 1 will be inverted to what? To 0. Okay? So this is how it works. So this is the truth table for the NAND gate. So this same thing will hold true for the NOR gate. And what is the NOR gate? The NOR gate is simply the addition of a NOT to the OR gate. Remember the symbol for OR? This is the symbol for OR. Okay, a 2-input OR, A and B. Then you put a circle here, that's a NOT. So the truth table for this, we take the same form or shape, A, B, A should be dots, sorry, because this is a NAND gate. So this is A plus B, A plus B bar. Okay. So this is 0, 0, 0, 1, 1, 0, 1, 1. These are possible values for a 2-input NOR gate. So these are the possible outputs for the OR. Now for NOT means inversion. So this will be inverted to this, 0 will become 1, 1 will become what? 0, 1 here will become what? 0, and here will become what? 0. So you can see it's like the opposite of this one. Almost opposite of this one. So you can see it. So this is the purpose of this NOT. So wherever the OR function is done, coming out from the output, it's what? It is inverted. So this is the truth table for the NOR and the NAND gates. Now let us look at the last two, the truth table for the last two, which is the XOR. The XOR. Remember how we draw them? Same thing like the OR gates. XOR. So the truth table still holds the same way, A and B, for all possible values of the XOR. We have 0, 0, 0, 1, 1, 0, and 1, 1. Okay? And then this can be used as a comparator when you don't want the output to be the same. Okay, that is, if the inputs are the same, your output is 0. If the inputs are the same, its output is 0. Okay, so if the inputs are the same, your output is 0. So this and this are the same, this and this are the same. So you have, this is the truth table. That's the truth table. 0, 1, 1. Then for that of the X NOR, two input X NOR. Remember how we draw it. This is the NOR. So we have the X NOR. AB 0, 0, 0, 1, 1, 0, 1, 1. So we have A, B. So it seems like the opposite of the other one. So which means just like inverting these answers. So 0 here you have 1, here you have 0, 0, 1. Remember, it has gone through the NOT. So that's the truth table for that. So that can be used as a comparator when you want the output to be the same. That is, if the inputs are the same, it outputs a 1. So if the inputs are the same, the output is 1. If the inputs are the same, but if it's not the same, you have a 0. So it can be used for so many applications, depending on what you want to achieve with it. So probably you're trying to compare the levels of a fluid and probably water in the tank, and you don't want them to be the same. Okay, so whenever they are not of the same, you have a 0. Wherever they are equal, you have a 1. And this logic 1 can mean a high, that is, turn on something. So it could be turning on an alarm, it could be turning on something, could be activating something else. So that is how these comparators, or rather these logic gates, work. So you have them, combinations of them, okay, in the form of an IC. Okay, when you go to the market looking for these things, you get to see them in an IC form with about 8 legs. So these are logic gates. Okay, so there are some examples you are going to try your hands on, like a quiz in your material. When you go through it, you will further familiarize yourself with the logic gates. Thank you very much for listening. Until we see you in the next class.